Thank you so much for your kind introduction. I will try to, well, to give my personal opinions on what is the evolution of prefabrication. This is where I have been working for a lot of my career. And I will try to give you what the ideas in the past have been and what I think is going to be the development in the present and in the future. Okay, so this is the title of the presentation. And I will start a little bit from the history. Even the first concrete or reinforced concrete elements were already precast, like this Lambeau boat. Of course, they were not for construction, but okay, we are going quite far in the past, but I am going to focus only in a few things of the past that give us some idea of the recent evolution of prefabrication. I will start first with the idea of pre-stressing. In the late 20s, Eugène Freycinet, this French engineer, managed to get this idea of pre-stressing and put them into practice. And he put them into practice because he developed many techniques to do that. And he did it in a precast factory he built himself. And that was the beginning of many practices for that. Some years later, he developed also post-tensioning. And I bring this bridge because it's an amazing bridge for the time in which you could really stress the cables to prepare to do this 55-meter span. This is a segmental bridge also, precast segmental bridge. So it's quite interesting to see how from the beginning, the evolution was very fast. He was thinking that pre-stressing had to be in the three directions. So this bridge is pre-stressed in all three directions, longitudinal, transversal, and vertical. And it's quite interesting how we have developed in other ways since then. And this has led into many other precast segmental bridges. And today we have many examples of the use of prefabrications in this kind of elements and bridges. And even full prefabrication of cable stay decks. And that means that you are combining pre-stressing and prefabrication or industrialization of concrete elements. That is how we could call it also. If we go to buildings, of course, there were many examples of precast buildings at the beginning of the 20th century, even in the 19th century. But I think the big boom of prefabrication in the 20th century was after the Second World War, and it was developed with what we call closed prefabrication. That means that it was all modular systems, all systems that were not being able to change anything in those systems, and that allowed with a minimum amount of elements, of different kind of elements, to build the very large millions of houses that were needed after the Second World War. And this was this concept of closed prefabrication that has come to our minds since then and has made some problems to the thinking of architects and engineers in that. Here is an example of these closed systems with everything fixed, everything modular, and everything, let's say, full prefabrication. No other kind of other elements or other type of materials there. And this was very good and very useful at the time, but the things have evolved a lot. But in the mind of some of our colleagues, we are thinking on prefabrication on this kind of closed fixed model or fixed system prefabrication. Since the 60s and 70s, slowly started to move into what we call flexible prefabrication, in which you could use pre-stress elements with traditional decks, for example, or try to do industrial buildings with, let's say, not so fixed elements. That meant that even some architects or architect contractors, they were using prefabrication for very different kind of constructions. For example, this is the Palazzetto dello Sport, the Nervi, from Nervi. that he used prefabrication because he was also a designer and a contractor, and he used prefabrication in the way to build this marvelous dome that is in Rome, and he used also in situ concrete to connect and to build all this structure. So with almost concepts of traditional prefabrications, we can also do very beautiful buildings and very beautiful constructions. There are many examples of this. And slowly, we moved from the 80s and the 90s and this century to what we call today open prefabrication. That means that prefabrication is not only fixed, is not only, let's say, try to use the same elements all the time, that now the most complicated parts of work are done in a factory, and they can be flexible with the molds, flexible with the production, and then even the economy can be done in a way that you can use many kinds of different types of elements, from structural to architectural, and we can get the best finishings and the most, let's say, complicated structures in that sense. And in this way, the evolution today is that by using pre-stressing, by using some kind of elements, like in this case, hollow core slabs, in some countries, they are using these long spans to create flexible environments. So the buildings, one of the problems that the buildings that we have today is that we demolish buildings that are in perfect shape from the maintenance point of view, but for the use, they cannot be longer used anymore. So this idea of long spans and flexible interiors are very important and are used in some countries. Of course, the examples that I'm showing are different country to country. This is an example from the Netherlands and the Nordic countries, using these long spans. Or we use these long spans that the pre-stressing allows in prefabrications to use these large industrial buildings, up to 40, 45 meter spans, 15, 20 meter columns, in some countries, these solutions are solved with steel, and in other countries, these solutions are solved with concrete, and many times with precast concrete. So this is the actual reality that we live in many countries, and as you can see that we can push these prefabrications in that way. And also in many countries, we also see used prefabrication for complicated buildings like these commercial buildings, in which they also are using mixed solutions with some parts of the precast made of precast concrete, some kinds in situ concrete, some kind steel, some kind even the closing in glass. So these more eclectic solutions today are, let's say, used everywhere. At the end, we are talking about an industrialization of the construction, and this industrialization of the construction can be used with many materials. And I think we are now not more monomaterial designers, and we are using the best materials for each part of the building. Here I show some examples of what the evolution of prefabrication in facades. It's incredible. Today you can find any kind of solution. There are specialized companies that do this kind of finishings. For example, here what you see is it's all precast concrete, some with brick, some with color concrete and form, and that appears to be wood is also concrete. So the finishings, the possibility of the finishings are very large, and we can really work with that. And I could say that the only limit to that, the possibilities that we have today, I could show many other examples, are the ability of the designers to imagine a solution that can be good for that. Also, from the structural point of view, prefabrication in the past was saying, no, you cannot use prefabrication in seismic areas. But this is not true. In the most seismic areas like New Zealand or Japan, they are using prefabrication for high-rise buildings. This is a more than 30-story building in Tokyo. So you could say the largest seismic places in Earth. And they are using a fully, well, not really fully, but almost fully precast building with precast column, precast beams, precast planks that are complemented with in situ concrete for the topping. So of course the connections become more complicated, but the benefits are immense. They are just halving the time of construction because using these industrialized solutions. So this is a good example of a high-rise building in seismic areas, or another example of 100-meter building in this case is in Europe with precast beam columns and slabs, but with an in situ core. And this is something that it's been done in many other places. Here is another example of a multi-story building with precast beams, slabs, but also using an in situ core. So you can see also that what we saw before of only straight elements, only elements of one size, here you can see the different kind of slabs, the beams that are curved, the adaptation, complete adaptation of the solution of the precast elements to the architecture and to the geometry of the building. And I want to bring another two examples. One in the north of Europe, they're very used to use panels as load-bearing panels, and this is another example. This is in Netherlands of a high-rise building, more than 100 meters high-rise building with made with panels. The structure of the bottom of the first floors are made with in situ concrete because of the height of the floors, but all the rest of the building is made with fully precast solution. Even the facade are coming with the panels, and the rate of construction is about 2 floors per week. So it's really very, very fast. The construction, and this is one of the important things of these constructions. Also that the ability that they are not using any space except for the footprint of the building. And the other example I bring is a building made of with precast beam columns frames, but in this case it's an inclined structure, quite complicated because you have to hold all these horizontal force that are coming from the inclined columns, and all this is also solved with a precast structure. So we can see that really we are today being able to solve many problems, and we are bringing this industrialization of construction into the building site. And now I will try to talk a little bit about what the FIB Commission 6 has published about prefabrication. I'm bringing just very shortly here some of the bulletins about hollow core slabs. There is in preparation another document on hollow core slabs, about mixed construction, that means with different materials, wood or situ concrete, or environmental aspects, and this is quite important. And the first precast bridges that was already some years ago, or railway systems, and two quite important documents that one is more for the producers and for the owners, how to treat imperfections, how to treat when you have a defect in an element, if it's important or not, how to solve it, what is the reason that it comes, and if you have to reject an element or not because of that. And the other document, which is quite important, is the one about connections, because in prefabrication, many things are about connections, how you solve the connections. And here is the basics on how to do the conceptual design of connections. Affordable housing, how to use prefabrication in emerging countries, or how to avoid any problems about robustness and all the connections to avoid any progressive collapse that it was in the past. And this 74, that is the Planning and Design Handbook, is being used by many universities to teach prefabrication, because it's a good conceptual design guide for the use of prefabrications in buildings. I know several universities that are using this document to allow students, and it's also good for architects or for people that are coming into prefabrication. You have the main concepts of designing with precast elements there. And some of the last ones are the precast concrete buildings in seismic areas, with a lot of detailing solutions on how to solve these connections, or the insulated sandwich panels, very important for the energy efficiency of the buildings, and how to solve the real sandwich panels that are very common in the Nordic countries in Europe, but not so common in the South, and how to do that. Or sustainability, that I will talk a little bit later. Or how to solve the continuity in precast bridges, as you know, is a quite complex calculation, and this is quite important to see that some of these documents are being done together with PCI, which this commission has a very good collaboration, and these documents are joint documents with PCI. And the last one published today, up to now, is the conceptual design of precast concrete bridges. And this is quite interesting because it shows about 30 examples of precast bridges all over the world with detailing, and to see how different communities, they do different kind of solutions. And this can give a lot of very good ideas to designers and to people that are looking for different solutions for that. The one that is in the oven now, that will be published soon, is the precast concrete in tall buildings, that hopefully we'll have it in the end of this year or beginning of next year. So this is about what is the information that you can get from the FIB directly. And now I will use my last minutes to tell you what is my personal feeling, how prefabrication is going to evolve in the next year, and it's already evolving. So this is something that is active in some cases in some countries, in some companies. So I think we already began the route to individualize production. I think lean production is industrialized construction. It's very important. That means that you build each individual element by itself, and you adapt each individual building element by itself. So you can really produce almost everything, almost with the same cost that you produce mass production. Mass production is already not being used even in the car industry or in many other industries, and this is coming slowly to other industries like prefabrication. So I think this is the first big concept that we have to know, is that we can adapt the construction of each element, and this is very important. The other important revolution is BIM, and I think BIM is being used in many countries, but this is a concept that has changed and will change. I will say a little bit later. Also, robotization. The use of machines, of course, is easier to use machines and robots in factories than in the work site. Also, industrialization will go to the work site, but in the factories, in prefabrication, in this case of concrete prefabrication, this will bring the use of these individualized elements in a more economic way. And then, of course, the introduction of installations, I will say something about that. And I think BIM will help to go in this direction and to add value to the structure, let's say, in that sense. And the use of new materials like composite solutions. And then I will say a little bit about sustainability. Okay, so BIM is a change in a concept. BIM, we can think about it as of drawing, but it's not that. Up to before BIM, we were drawing, we could say like the Romans, we were drawing lines, and we were drawing lines with computers, but drawing lines. And from here, we are working with objects, 3D objects, and these objects are becoming a database, and this database allows to the interaction of different activities in the workplace. And this solves one of the big setbacks that the prefabrication had in the past, that if you go to a work site, before you had a project and you were adapting that project all over the work of that. And now, if you work with BIM, every industry is working with the same model, everybody can adapt to that model, and you have to prepare in advance. And if you prepare in advance, this is what prefabrication needs. This is what industrialization needs. And this is, I believe that this is coming into the industry, and this will make the construction industrialized in many, many ways. I'm talking about prefabrication, but this is going to be in many ways, and this will help to prepare in advance everything in factories and assemble them very quickly and very efficiently in the work site. Of course, you can go further than design. You go into the reinforcement, you go into the installations, you go into the schedule of everything is in database, the schedule, the economics, and the possibilities are very, very big. So I think this push of BIM will push industrialization, and this will push all kinds of industrialized constructions in the work site, among them prefabrication. So this is, I think, from my point of view, very, very important. And this allows also to individualize these elements, and to individualize these elements, you can use robots in the factories. Today, these are pictures of today. We are using already robots in the factories for placing of reinforcement, for the shuttering, for cleaning, for some kind of elements. But this will slowly evolve and be used for more and more complicated elements. And I think that these robotizations will slowly come. Up to now, we are, let's say, manually doing things, but flexibility and robotizations will help produce these individualized elements in a more economic way. The other thing that can come to our minds is 3D. Everybody's talking about 3D. We don't know what is the reality of 3D in the next 10 years. We really don't know. There is a lot of tests. I'm going to show you some of the ideas. But what I am pretty sure is that it will be used first in industrialized ways in the precast factories, because in small sizes and in precast factories. But still, we don't know yet what's going on. Dubai is pushing 3D and all these automatizations in a way. So this is an example of what they have done. They have developed these buildings that they have built. I have seen them. And what they have done, they have developed a structural, let's say, 3D printing that they did in China. And they transported the elements from China, not very sustainable, but in any case, done in a factory, did a research to introduce the reinforcement and to do the load tests, and then to finish let's say the buildings. Very specific buildings is a good test. We don't know what will be in the future, but this is an interesting idea. Other ideas, this is from Eindhoven. They're doing segments of a segmental bridge that is post-tension afterward. This is a small pedestrian bridge, but this is another interesting idea. The problem of introducing reinforcement, longitudinal reinforcement in 3D printing can be solved by creating segments and post-tension those segments. Okay, this is another quite interesting idea. Or the idea to create forms that are very, very free. For example, like these kinds of solutions that they've done in Eindhoven. We creating first the forms and then adapting the 3D printing to that form, which is then you can create these very interesting shells. Shells stop to be produced in our world because of the cost of manpower. But now maybe this manpower can be, this cost can be solved, and we can go back to this very efficient and in this case very sustainable elements because they use very little materials. Or this example that is from the US, that they are not 3D printing concrete, but they are 3D printing plastic to use it for the molds. So you can really do very, very different elements and adapt every element because you are using the 3D production, not in the concrete, but in the molds. And this is also very interesting. Other important thing is how to use the installations within the concrete, within the structure. That will raise the added value in the structures for sure. And in prefabrications, I think This is already examples, but I think BIM will help to produce these structures and these elements in a more way. And then use also the thermal mass of the concrete and try to make the structure not a passive element, but an active element. And this can be used with in situ, with precast, but this is one of the future that I think for energy efficiency, they will be very important in the future. And then the new materials, the ultra high performance fiber reinforced concrete. I show you some examples. This is a 100-meter segmental bridge, precast bridge in Malaysia, done without shear reinforcement. They have done hundreds of bridges, not like this, smaller than that, but quite interesting. And these are solutions that are not possible in Europe because of our regulations, but they are showing the way. But also with these ultra high performance materials, you can do very thin elements, very interesting solutions for architectures. This is another example for architecture. And then the material brings you another possibilities. Or this bridge that was designed in the beginning with a steel deck and then was passed and was changed for ultra high performance concrete precast elements, and they decided to do it because of durability, maintenance, and also the weight is very, very similar as of steel, which is quite interesting. Or an evolution that it's there, and it will come in the next years. That is the evolution is what we call carbon concrete. That means that taking steel out of the concrete, then reducing covers, and then if we reduce covers, we can do very light elements. And very light elements means less use of materials, more sustainability. I think it's quite interesting that the evolution of these elements will be in the precast industry. And then I have only four slides to talk a little bit about sustainability, because today's topic is a little bit about sustainability. Some of the important topics in sustainability is to use less materials and local materials. And this is done normally by force in precast industry, because you have to use less materials because you have to transport to the site. And normally you're using local materials from the quarries and from the cement. So all this is quite in the line of sustainability. And also the reducing of waste, the ability that you're in a factory, you can recycle aggregates. In some countries, they're recycling more than 50% of the aggregates and even the water. Yeah? So this is quite important. And you can do that quite well in the factories. Okay, and of course, all you need that because you have a quality assurance, you reduce your tolerances, and then you can go with very thin elements. And these thin elements can even be thinner if you're using this ultra high performance concrete and without steel, in some cases, with other kinds of materials like carbon or many other solutions. And all this is a table from the Bulletin 88 that is talking about sustainability, and in the FIB Commission 6, we are talking a lot about sustainability and how to deal not only with CO2, but with all the three pillars of sustainability. And that means economic, environmental, and social, and how to allow owners and even all stakeholders how to decide how to build, taking into account all these three pillars, and how to evaluate that. And we are developing these methods to help all stakeholders to try to see how they will decide to do their own buildings. And I think all around sustainability is very important that engineers and structural engineers are involved in this, because the decisions in the future will be taken about sustainability, and we need to be there in one sense to see that there is a philosophy behind and not just greenwashing concepts. Okay, so this was my ideas, and thank you for being there. A lot of people I can see, and I'll be happy to answer any questions from you.
Thank you ever so much, David. That was brilliant. I mean, just as the title of your presentation said, that was a fantastic tour around the past, the present, and the future of prefabrication. Can I just remind everybody, if you're asking a question, can you please make sure that you rename yourself as a full name so I can see who's asking questions. David, I mean, you finished around sustainability there. And obviously our current president, Akio Kasuga, has very much sort of set the agenda for sustainability. Yeah. I wonder, is there any more you can say about what FIB is doing in terms of perhaps sort of future publications around sustainability, particularly around precast structures? Yeah.
Well, I can say, Nadia, you say Akio Kasuga is the FIB president from Japan. And he is set up an agenda to focus in sustainability for the FIB. Well, I can say that, for example, the model code that we are finishing, hopefully presenting to everybody next year, the main let's say concepts are the overarching concepts are about sustainability and leading sustainability and to deal with that and then take it all the way down. So this is important. Then we also in the FIB, we have produced a statement of sustainability that we have published in the journal that is publicly available. And if I'll be happy to send it to anyone or through Chris, we have it public also in the webpage. So the position of FIB is clearly to evaluate sustainability and to help the concrete structures community to evaluate that, because there is many information around there, but not so clear and not so clear guidelines for that. So we are working very hard with Akio to try to put the main important information available for everybody that they can take it from the FIB. And this is quite important, I think, and we'll be happy to have anybody on board to work in this direction. And regarding the prefabrication, we have a group that is working that had this publication 88, and now we're working to apply these methods of evaluating sustainability on a real building. And we are working and we'll try to publish a document on how to evaluate with an example of how to evaluate sustainability for a building. This is our ideas now.
Fantastic. I'm going to come back to precast in just a second. Jane Black has asked, how big can 3D printing go? Is there a limit on the size of the buildings that can be printed? So I suppose she's asking, examples of the sort of largest structures that perhaps you're aware of.
Well, I know there are printers that are about 5 meters by 5 meters, so I can even printers that go to the site also. So for me, this is I don't know, this is a technique that is evolving. That today for me it's hard to tell which will be the final solution, but I'm sure there will be some solutions. So I'm sure that we'll have that around in our daily work, maybe in 10 years.
Excellent, thank you very much. I mean, I'm a bridge engineer, as you know, David, and so it's been great to see some publications around continuity of precast bridge beams, for example, to sort of get a good degree of sort of standardization in the industry there. One other problem, that we face in the UK certainly is actually with steel concrete composite bridges, but a drive to move more to full depth precast concrete deck slabs, to try to reduce the amount of wet trades. And a significant challenge is making the joints, the stitch between the two, as small as possible. Mm-hmm. And there's lots of sort of, I guess, possible solutions there with ultra high performance concrete to limit the length of laps or to use the interlocking U-bars. But a lot of these solutions, our clients are still quite nervous about because of lack of many applications. And I wondered, is FIB looking to produce any sort of guidance around that? Well,
the task group 6.5 about precast concrete is working on a document on ultra high performance concrete in bridges, in precast bridges. There are solutions for all very small overlappings in full depth concrete slabs. And there are some applications in the US, and there is something in Japan also. And there are different applications. I think every country has different solutions, and this is quite interesting. But because you can see what other people do, and then you can get your own solution. You don't have to copy. You can just use your own solution. But yes, if you would like to, I can get you in contact with this group, and there is an ongoing work now on this ultra high performance concrete in bridges.
Fantastic. I think we just got probably time for just one more. It's actually coming through the chat pane rather than the Q&A box. But Maggie in Dubai says that she loves the thought of eliminating shear reinforcement in concrete using high strength concrete. Is this something that we're going to hear more about through FIB?
We do not have that like a solution, but you will have in the model code solutions for shear with fibers. Of course, this has to be ultra high performance concrete with fibers. This concrete that I show you has about 1.5% of fibers, and so yeah, this is clear that you can do it. But as you know, bridge engineers are quite let's say conservative, or the administrations on each country is different. So I don't know. I think it's good if you're a bridge engineer and you want to do things in ultra high performance concrete to do a travel when it's possible to Malaysia. I've seen bridges from 20 meters to 40 meters without any problem. Yeah? And of course, examples are important, but I, for example, I do not see that in Europe for now because of the regulations. But I can see that in buildings or in let's say static places where you have static loads.
Thanks very much. We just started to attract a load of questions. Just a couple. We do have some time. Ricardo Strocios asks or says the current trend seems to be to optimize the size, thickness of elements driven from a sustainability point of view. What is the FIB view or planning new design guidance on finding the fine balance between optimizing the section and maintaining robustness and durability for not compromising the design life of future structures?
Well, this is something that you have to ask yourself in every work. There is no universal solution for that. So if you can, I mean, there is one thing is very important is that if you reduce materials, you reduce CO2 and you reduce the impact in the environment. And this is very clear. And this is everywhere. I mean, there has been comparisons of for example, the same columns in concrete that is 30 or 35 with the same column with a concrete of 80 and which they are smaller, even if you have per cubic meter more cement or more materials or high quality materials, at the end, the impact on the society and the impact on the CO2 is less. So of course you need durability, but if you have high-end concretes, you have better durability. Imagine that you change steel for other elements and that you don't need such a big covers like 3, 4, 5 centimeters as you have today. That is material that is just to protect the steel. So all this will evolve. This is not today, but the trend is in this direction from my point of view. And designers have a lot to say because you can, I mean, I think today with a proper view, without not many more techniques, you can reduce about 50% of the CO2 in your building if you are designing looking for these things.
Lovely. That's fantastic. I could probably take one more. It will have to be really, really quick though, David, because we've got like 1 minute left.
Yeah, okay.
Stuart Matthews says, very good overview and future look. Can anything be said about the future linking of precast with performance-based specification?
Well, I would love to see that in the short future. It's not clearly today in the model code, but I hope in the future model codes it is. Today, performance-based, it's basically focused on materials, but I think there is a huge possibilities for performance-based design in precast elements. For example, what the question we had before about shear reinforcement, if you can really have a performance-based design element, then you can design as you like. You don't have to follow these strict conservative normatives. So for me, it's a big step ahead. It would be a big step ahead.
David, thanks ever so much. I mean, that's really great. We did have another question, but we'll have to speak to the events team to see if we can get it sort of forwarded to you and answered a different way. But thank you ever so much for taking the time to share your experiences with us. It was really much appreciated.
Okay, thank you, and success for this event. That is, I can see it's already there.
Thank you very much.